Are we sure that it's in this meeting room?
I don't know. I went into my email to see if there was a message about meeting in one of their rooms. I didn't see anything. There also weren't any announcements in Canvas, so I just assumed it would be here.
Okay, let's see. I'll just text Jim. Hi, Jim.
Hey, I don't know. Where is he?
Where are you?
Well, I'm in my house.
Are you coming to the Zoom meeting?
I'm trying.
Okay.
Are you in there?
Yeah, I've got some.
Where's he?
Not here.
Oh, dear.
Oh, here he is. Okay.
If I can figure out how to get there, I'll get there.
Okay. Canvas, Zoom, click on the meeting.
All right, I didn't see it when I was there before.
I promise it's there.
Bye.
Bye.
Yeah, half a teaspoon. Hello? Guys hear me?
I can hear it.
Anya, I think you had to be the one to start recording. You're running the room, right?
Yeah, it should automatically be, yeah, it's already recording.
Okay.
Yep.
Is Jim here yet?
Jim who?
Jim Ho.
Jim right
Gymnasium.
or Jim wrong?
Jim wrong. Gymnasium.
Gymnasium is in the room.
Oh, he is. Okay. Oh, there he is. Tell everybody what your background is. You
You
grew
tell
up in
me.
West
I don't know,
Virginia.
it's-
No.
Mud.
Oh, the one behind you. What is it?
It is a sedimentary rock that I found online. You tell me it's from the coast of Dorset,
What I think it looks
and
like.
it shows interbedded clays and sands, I think, with soft sediment deformation.
Yeah.
I'm pretty sure that's what it is.
If you can find out where it is, I'd be curious. All right. So everybody ready? We're going to have a bit of a lecture before we start into the actual field trip. So most of you are residing in this red box, which is the Newark Basin, which is a physiographic province in New Jersey, sometimes called the Piedmont. The Piedmont has different meanings. And the Newark Basin contains a series of mostly upper Triassic, but some lower Jurassic. And the light blue here is Triassic. This greenish color here is Jurassic. And the reds, of course, are the various kinds of extrusives. These are the Watchung Mountains, first Watchung, second Watchung, third Watchung, and of course flows. And we have the Palisade Sill coming here, and then the Lambertville Sill, and we'll be visiting this little place here called the Byram Sill. So there's various kinds of sills that make up this basin. It's most of urban New Jersey is underlined, including New Brunswick and Trenton, are underlain by the so-called Piedmont, sometimes called Triassic, Jurassic lowlands, or most properly geologically is the Newark Basin. So the Newark Basin shown here in the past, it was at lower latitudes. We'll talk about that in just a second, but you can see here's the equator. So the rocks that we're looking at, in round numbers, keep the number 200 million in your head. The precise number is between 198 at the youngest part to about 230 or 235 in the older part, a million years ago. And again, this is late Triassic to early Jurassic, and it's at fairly low latitudes, a dry belt actually. Remember that around 30 degrees to 20 degrees, and actually closer to 15 degrees north and south is where it's quite dry. So this is a paleo dry belt. The Newark is a rift basin and will be a basin something like this. This is showing you, so what rifting is stretching of crust. Stretching a crust forms a series of, well, these are essentially half grabens. Technically, this one's a graben here because this one's moving down, this one's moving down. But over here, you're just looking at half of the graben. Okay. This occurs often prior to seafloor spreading beginning. So that's what's shown in this cartoon, is moving from rifting to formation of new ocean crust. And that's what happened around here with the birth of the Atlantic. But what happened in the East African Rift Valley is that there's been no seafloor spreading, and it's occurred, and nor is it likely to perhaps be. So it's a failed rift in the sense that rifting did not lead to ocean crust formation. Again, these are described as half grabens. So we have a normal border fault on the one side, typically in our region to the northwest. we have the base of the basin, and we have, of course, the top. And this forms like triangular geometry bordered with this border fault, which is why it's called the border fault, with an uplifted footwall and a down-thrown block here, the hanging wall. The hanging wall very often will contain lakes, okay, as is typical. So today, this could be Lake Tanganyika with a huge fault scarp to the northwest, and then a lake, a very deep lake, in the case of Tanganyika, over 800 meters deep. So the Newark Basin is one of several rift basins. The largest of exposed rift basins is called the Newark. It connects through to the Gettysburg and the Culpeper, and you have the Taylorsville, Danville Basin and basins to the south. And to the north, we have the Hartford Basin here, and the Fundy Basin here, and offshore basins off of Canada, including the Orpheus and Jeanne d'Arc Basin. There's also offshore buried rift basins that occur here that have been mapped on seismic profile, but of course never sampled because they're very deeply buried. Again, these basins, this is the names of the basins shown here again that I took you through. This is the grain of the Appalachians. The border fault on these basins follows the trend of this Appalachian mountain chain, this Appalachian origin, as we call it. The border faults are commonly reactivated Paleozoic faults. So there are planes of weakness that formed when the Appalachians were thrust together, only to, when extension began, they began to fail along the same planes. And I should note, and I'll come back to it, that these faults are what's called listric normal faults. So this block is moving up and this block's moving down, but not shown here, and we'll see it in a minute. This fault comes down and dies off at depth, and that's called a listric fault. Look here at the Newark Basin. It says against age. What I just said is that here we go. We have a threefold subdivision, basically. We have the oldest strata, okay, which are part of the Carnian stage of the Triassic, are fluvial. Then we have deeper water lakes here, and then shallower water lakes here. These are capped in the Triassic by the flows of the so-called camp basalts, Central Atlantic Magmatic Province, which includes the Watchung Mountains and the associated intrusives like the Palisades, and then overlain by, again, a series of lakes, shallow lakes here in the Newark. So some of the basins go a bit younger. The Hartford goes a little bit younger. Some of the basins stop rifting significantly older than the Newark. So as we go south, south is to the left, Culpeper, Taylorsville, Richmond, you can see that the strata don't get any younger than about 210 million. If we go to the north, the Hartford continued to have sediments to about 195. So Ronan, I'm going to ask you, when did rifting end and when did seafloor spreading begin?
The rifting ended at like 230 to 220 million years ago.
No, look at the figure. It went to 195. This is still a rift basin here at Hartford.
Oh, okay.
Okay, so when did seafloor spreading begin?
About 180 million years ago.
Yeah, somewhere between 180 and maybe it may have not been a synchronous event. It may have occurred diachronously. Martha believes, Martha Whitjack has written a paper. It's not a belief, it's provided evidence. So it's not a belief at all. It's her interpretation that seafloor spreading began in the south initially, and the basin, the North Atlantic Basin opened, the North Atlantic Ocean opened like a giant zipper from the south toward the north. This is a great reconstruction because it puts the paleolatitudes and longitudes into perspective in the Atlantic. We think of the Atlantic as east-west spreading for the most part, right? But in fact, this reconstruction with a fixed position here is showing you there's a significant northern component to the drifting of the basin. Later on, it is more east-west, but certainly as we saw the beginning of this, let me just start it over again so you follow along. There, we're having rifting, formation of these rift basins. That's the yellows. And then we have seafloor spreading. and forming ocean crust. And you can see the northern component. I hesitate to show this figure. It's complicated, but it's genius. And so to a certain extent, it's really simple. There's a time scale here. This is the Newark Basin, MB here. It's showing the same strata I showed before, okay, which is this column. This is another way to show the same thing. So get your mind around that. So we have the fluvial sediments, we call the Stockton. We have the deep lake, which we call the Locaton, and the shallow lake called the Passaic. Superimposed on these are lines of latitude, and because the basin's moving northward, they change through time. And so we can say, during the Locaton deposition, what was the paleo latitude? So this is the Locaton here. Those are those deep lakes. And it was about 10 to about maybe even 5 degrees north. And as it moved further to the north, it moved into the younger strata, the basin actually did move further to the north, and it came more in the subtropical dry belt. By the way, what this predicts is that anything in this 0 to 5 to 8 degrees even is fairly wet. This is Africa today. This is showing you the evaporation precipitation balance over Africa today. So there's the equator. And you can see there's the Sahara. So the Sahara is centered at 23.5 degrees north. So when Professor Jim gave his lecture about deserts, we say, yeah, it's 30 degrees north and south. You know, that's more or less true, but it's actually centered at about 23.5. Okay, not far off of the tropic. You can see that the boundary between the two is at about actually 12 degrees north. And that's today, and 10 degrees south today. And so again, that's what's been colored here, is that the green is the prediction that it's fairly wet, and the yellow is a prediction it's fairly dry. So this is a way, I think, a really cool way to look at this and get a lot of information and makes predictions. So again, it predicts that these sections, this is Fundy, this is Greenland, I believe, saying that at the same time that we had these shallow lakes in New Jersey, that we had deeper lakes in Greenland because they were higher latitude and in the wet belt up here. So this is the classic geological map. It shows a border fault. It shows the strata here, with green being Stockton, purple being Locaton, and this being the Passaic Formation. This is the first Watchung. This magenta is the second Watchung. This purple is the third Watchung. So the stuff in this kidney here, this kidney shape, it is basically Jurassic strata. There are these major border faults that we'll take you through, and these intrabasinal faults called the Hopewell Fault and the Flemington Fault that are important in the basin. And we'll take you through those. So I always had to orient myself on the Delaware River. So this is the Delaware River. This is the Delaware River. These are the Newark Basin core holes I introduced you to. So Martinsville is here. Princeton is there. Livingston, Kilmer campus is there. Somerset's there. Titusville and Nursery Road are here. There's the Princeton one right there. I'm sorry, that's Princeton. Just jumping around. And again, this is the reds are in this case, the sills. This is the Palisade sill. This is the Lambertville sill. This is ringing rocks. So again, this is syn rift sedimentation. We touched on this. That means that sedimentation is occurring at the same time that there's movement along these faults. This somewhat controversial hypothesis was put forth, but certainly promulgated by our own Roy Schlisse. There are people who didn't believe that, and Roy produced, it's not a matter of belief, it's a matter of data. Roy produced data that shows thickening into the faults. So the sections that we will see on our field trip, we actually are starting just off of the border fault in the north and working to the south. As we move further away from the border, the sections thin a bit. And Roy was able to show that and show that this is, in fact, syn rift sedimentation. Again, these are half grabens with thick deposits in them. So the Newark Basin has about 6 kilometers of sediment. And if you actually take that and say how much was originally there, those muds compacted quite a bit. There was probably over 10 kilometers of sediments. But what's Martha Whitjack has taken that another order and shown that there's been erosion of probably an additional 5 or 6 kilometers or more of sediments that were originally there. So this is a boatload of sediments. Okay. Again, this is from the show The Border Fault. And this is segmented, as Roy says. So what's shown here is between the segments. This portion is called the Ramapo Fault. And this is another segment of the Border Fault. And you can see that this is going to be relevant to where we are. And in sections here, these relay ramps, this is the uplifted block here. This is the downthrown block, so the footwall. So basically rivers and other sediment sources, that is to say things like alluvial fans, come in and they come into the basin off of these highlands formed by the fault scarp through these relay ramps, as they're called. So that's what's important. We'll see this later. When I use the word relay ramp, you should realize that you have these slightly overlapping fault segments, but these are areas where the rivers and other sources of sediments can easily come in, as opposed to essentially these cliffs that are formed by the fault. There is some seismicity on this fault. On the border fault, this is another image showing that segmented border fault. And there are magnitudes typically on the order of 3 on the Richter scale associated with this. So it's just, New Jersey's not completely aseismic. The Hopewell and the Flemington faults are both have up to 3 kilometers of displacement vertically. Again, these are normal faults. There are some strike slip component to them. There is some folding in the basin as shown in here. And if you go back to the geological map, you can probably see it even better. Well, there's the picking out here. You can see it in some of the maps that is folding. Not a lot. Okay, but you have these large interbasinal faults, which break up the basin today into a few fault scarps, and we'll see that. This is the Hopewell Fault picture taken by Don Monteverdi in the New Jersey Geological and Water Survey, showing you as we animated this fault near Hopewell, New Jersey. So I'm sitting about 4 miles away from this fault. And we're going to look at these half grabens. So this is section AA prime going through essentially New Brunswick, New Jersey. And you can see the border fault, okay, the Ramapo in this case, the Stockton, the Locaton, the Passaic. And so these are some sills that are going through. Okay, you can see those beautifully on seismic. If we take a section through over here to the west, again, the river being somewhere in here, you have 3 segments. So if we were going on this field trip for real, we'd be starting near the town of Stockton and moving up along the Delaware River to basically Milford, Stockton, Frenchtown, Milford. And we'd be going essentially across 2 of these faults. And as we got north of the Flemington Furlong Fault, right at Route 202, we'd come from 1 block. So 202 would come in here, just south of Stockton. We had the town of Stockton, and then Stockton sees an outcrop of, guess what formation? Stockton. And then we move to the north, we see the Locaton and the Passaic. And we're going to do this trip backwards this time. We're going to start in the north and work our way to the south. Normally we just, for ease and for stratigraphic simplicity, we start in the south. We've done a lot of our, because it's such a spectacular outcrop up here at a place called Pebble Bluff, we put together our YouTube video for that in the north. I mentioned the seismic. This is called the NORPAC line. It parallels the Delaware River. Here's the Delaware River. There's the NORPAC line. This is the border fault. You can see it dying out at depth. This is a listric normal fault. We can see the Passaic, Locaton, the Stockton, and actually a unit below it that has not been sampled. And this is showing the more or less threefold subdivision of Stockton, Locaton, and then Passaic formations. And this is the core holes transect that we looked at before of this block. Again, the cores are fantastic representation. The outcrops are really good. I mean, they are not bad. There's the one at Pebble Bluff is spectacular. The little ones we were crawling around this week, the one on the Locaton used to expose the entire section pretty well. And we're going to look at that as best we can. But the advantage of these cores is you get a complete representation, all 25,000 feet of cores, multiply sampled the basin, and you get unweathered material. And you don't have to worry about what you're looking at. You know that this is the original unweathered material. And from this, we put together a section. This is in feet. So there's 22,000 feet starting at, here's the Orange Mountain basalt, which is the first Watchung Mountain as a name for formation. I won't test you on it, but it's called the Orange Mountain basalt. It's underlain by the Passaic Formation, which is shown in reds, purples, and a few grays. The Locaton, which is shown mostly in blacks and purples. You've already seen those different kinds of rocks, and we'll go back over them. And the Stockton, which again, these are mostly sandstones. Now you can see this column here. This is what's interesting. So this is a column with coarse sand, medium sand, fine sand, mud. And you can see that most of the basin, or at least 18,000 feet of it, is in really, you could argue, boring mudstones if you don't like mud. They're actually very interesting. They show a pattern of repetition. But if you like sandstones, you come down here and you have more sandstones than shales. But there are shales, and we will see the shales in here. Okay, in fact, I have one sitting right next to me that I picked out from this section on Thursday. The strategy for the Newark Basin drilling project, instead of going drill, we could go to Martinsville and drill a 25,000 foot hole. And that would probably be about $60 million, okay, in round numbers. Or we could go drill 3,000 feet at Martinsburg, drive to the south, drill 3,000 feet at Weston Canal, drive to the south, drill 3,000 feet at Somerset, drive to the south, and continue to do this and composite these. And that's what this is showing. So Princeton core hole was 3,000 feet. Showing more here, but it's 3,000 feet, and 3,000 feet of Nursery Road tight, and they overlapped so as to make sure that they completely sampled the section. And again, this is all of the Triassic. The Jurassic doesn't begin above the first Martinsville, and of course they drilled at Martinsville through the sill and into the upper Passaic. So there's no Jurassic straight in this Newark Basin drilling project. Oh, by the way, I should mention that the Orange Mountain basalt, 2 precessional cycles below the basalt, which is about 10 meters, okay, is the Triassic-Jurassic mass extinction, the number 3 on the hit list of mass extinctions on Earth. And we're not going to talk about that today. We're going to focus in on some other stories, but it's a great story. The Jurassic section is represented. This is a series of core holes, shorter, drilled for the Passaic Tunnel Project by the ACE. ACE is your helpful hardware man. It's also the Army Corps of Engineers. So the Army Corps drilled these, and these exist in our core repository as the ACE cores. We have 17,000 feet of these ACE cores. They sampled the basalts. So there's the 3 basalts. The first Watchung is called the Orange Mountain. The second Watchung is called the Preakness. The third Watchung is called the Hook Mountain. You don't need to remember that. I can't even remember the name of the interbedded formations, the Feltville, Tawako, and Booton. Again, it's like your cousins that you never see. I never see the Feltville. I guess I could go pull it out and look at it in the core repository. There are some interesting stories here. One thing I will say, though, is that in terms, even though this is 17,000 feet and this is 25,000 feet, This represents, we said this is about 230 or 235 million to 200 million. So let's call it 30 million. Okay, Ronan, is that okay? 30 million, 230 to 200. Okay. This, it's got no age on it, but I can tell you it's 2 million years. And this section is now plotted. This is not in feet, but I believe this is in meters. So this is a mile, baby. So this is, 3 miles, a mile of sediments, basically. So 5,000 feet in 2 million years. So 1,500 meters or 750 meters for each million years. This is a bit slower. 30 million years and 30,000 feet is 10 kilometers. So it's 10 kilometers divided by 30 million years. So that's a bit slower sedimentation rate. So the sedimentation rate picks up. So even though the section is thicker, it doesn't represent as much time. Not thicker, about the same. So the real story here is lake level cycles. And we went through this. This is the deep lakes shown by the black shales, then the gray shales, and then the purple shales. So this is deep lake, not so deep lake, shallower lake, as shown in this core. Paul Olson put together a beautiful depth ranking. One of our own graduate students right now, Chris Rowan, is doing this for cores drilled in the African, well, they're not lakes anymore. We've drilled Lake Malawi and gotten similar facies within the lake, but he's working on Lake Turkana. And so he's looking at ancient strata that are now exposed on land that were drilled in the past few years. And he's putting together a very similar depth ranking. So micro-laminated sediments are the deepest. These are ones that there's no oxygen in the lake. There's no burrowing organisms to break it up. There's no bioturbation. The lake is anoxic. There may be some fish swimming around in the lake above the anoxic zone, like in the Black Sea today. This top 200 meters of the Black Sea have oxygen in them, but the bottom from the 200 meters down does not. So it's an anoxic lake. And some of the African lakes today show that same kind of pattern. Then finally, laminated mudstones are a little bit deeper. Non-mud cracked mudstones are showing that the lake is staying wet throughout the year. The mud cracked mudstones are showing that the lake is perennially, annually, perhaps dried out. Then breccia fabric means it's wet and it's dry and then it's wet. And intense breccia fabric means it's only wet once in a while. It's basically a mud flat. So those are your depth scales. This is mostly a deep lake. This is the Lakaton. You can see the cycles. We'll take you through those. This is a blow up of that. So from black shale to black shale, that's a 20,000 year cycle. From not as black shales, coming back into the black shales again, is more 20,000 year cycles. Altogether, to go from very deep lake here to pretty deep lake here to not so deep lake here to, there's cycles in between. We'll go deep, shallow, deep. But you can see this goes from deep, the general lakes not so deep, shallow, deeper, deep. This pattern here is 100,000 year. This pattern here is 20,000 year. And there is a 400,000 year, 405 to be precise, that modulates it all. We will do this after Thanksgiving in detail, but you guys know enough about, you've heard about Milankovitch. And it's pretty simple. You need to remember 20, 40, 100, 400. So the 100 and 400 are eccentricity. How elliptical is the Earth's orbit? It varies from zero ellipticalness, ellipsoidalness, that's the right word, is eccentricity. Okay, that means eccentricity is the right word. There's no word called ellipsoidalness. Okay, it's zero eccentricity to 7% eccentricity. Okay, Precession, the Earth wobbles slightly on its axis and precesses like a top. I will take you through what this means in a more detailed lecture, but just remember precession, wobble, 20. Got that? Precession, wobble, 20. Eccentricity, okay, how circular it is, 100 and 400. Okay, you don't have to worry that it's 93 and 120, 95 and 123. You don't have to worry that precession really is 19 and 23 today, because it does vary, and we can talk all about that. So these lake level cycles record these various scales. I already went through this, but basically on the, let's say 5-meter scale, we go from black shales to gray shales to maybe purple shales, and that cycle repeats, and that's 20,000. These bundle together, so this is showing you a deep lake, deep lake, deep lake, deep lake. So you have 1, 2, 3, 4. This is essentially the 100,000-year cycle. And they compound together, bundle together is the right word. So here's a 100,000-year cycle, here's a 100,000-year cycle, here's a 100,000-year cycle, and they bundle together into this 400,000. So I mentioned this before, what's really a kind of a really strange thought. You know, in stratigraphy, we have formations. So we have this Passaic formation, and it's broken out and mapped as members. And these are mappable. You can see these on the map. If we were in the classroom right now, I'd point to the geological map and say, "Ah, I see all these beds." So a member which occurs occurs on our campus, actually, or across the river, beneath Antilles Field, is a Percy member. On our campus, we have the Kilmer, Livingston, and Mettler's member, okay? But the Percy member, which is exposed behind the Exxon station on Route 18, just beneath the Antilles Field of Douglas, is this member here. So it's a little bit older than what we have on our side of the river. These members are the 400,000 year. And we're going to look at this Percy member in the field. And we're going to look at one from the Locaton, which is called the Skunk Hollow. Or if you're from Virginia, West Virginia, what would you call it, Jim? Skunk Holler? The Skunk Holler Formation, or member. So we will look at this. This is the Skunk Holler right here. I got to be able to move something and see it. Here we go. So the Skunk Hollow member is here, and we will look at this part of the Skunk Hollow member. So remember that depth ranking? So 6 is the black shales. Okay, so we get black shales in a couple places in the Skunk Hollow, and we'll look at those black shales. And you will go through this section. I will give you the Skunk Hollow member and have you actually measure a couple of these cycles. These are the 20s from here to here to here. These are the 100s. Everybody following along? And this is the 400. And so what I said about the 400, 405 to be precise, 400 is good enough for government work. Those are the members, okay, that were recognized. So Milankovitch was live and well and controlling the deposition of these sediments. And Milankovitch isn't something magical. Named after a Serbian mathematician who first figured out these beats in the Earth's orbit. And he postulated they control the ice ages, and they do, okay? But they also control the amount of rain, particularly in low latitudes, particularly in places with large continents like Tibet and Asia. So what's controlling these lakes is what we would call E to P, which is a fancy way to say it rains like hell and then it's drier. Rains like hell, then it's drier. Rains like hell, then it's drier. I mean, for periods of time. And so we'll go through this when we discuss climate. But if you take this section and compute what are the dominant beats in here? Okay, the dominant beats in here, there's one that's around 5 or 6 meters. Okay, there's one that's around 24 meters. There's one that's around 100 meters. And Paul Olson, who's at Lamont Doherty, he grew up in this basin. He used to ride his bike to collect dinosaur bones, and now a famous locality right off of the New Jersey Turnpike up there called Fraternity Rock. And there's some exposures with dinosaurs. He made his bones, so to speak, figuring out this cyclicity. Everybody saw cycles, but nobody could prove that they had any real beat. And he did that. And I'll take you through that some more. But again, here we'll look at this in a core. This is the Locaton. This is probably the best way to do it. You've looked at this a little bit. So this is the deep lake. We come down this core. So there's 3 feet, 6 feet, 9 feet, 10 feet, maybe 11 feet. So a little less than 4 meters for this cycle. And then even in these really boring red beds, okay, actually the best outcrop I've ever seen, one of the best examples I've ever seen of this cyclicity in the red beds of the Passaic is at Pebble Bluff, and we videotaped it for you. It's even better than I can see in these cores. But these cores, again, show, you know, you have the reddest stuff is the most exposed, most oxidized, okay, the least oxidized here, and then it goes red again. So you can see even in here that it's going from very shallow evaporated playa lake. Playa is a good word. It evaporates and isn't around all the time, to a shallow lake and back to a playa lake. And again, this is 1, 2, 3, 10, 12 feet. And we can see those. This is on Route 202, just south of Stockton, actually. And Roy Schlissa took this and did a nice job. This is now pretty overgrown, and I was here just the other day, and it's completely covered with poison ivy. So it's not too bad now because it's all the leaves are dead, but it's now covered, so we don't go here anymore. So again, the examples that we went through, and I'm just about done with this. I'm just showing you again what I showed you before. The examples from, we have the camp basalts, which are the Watchung Mountains, the diabase, or sometimes called dolerite sills, which you can see the grains, the Palisades, the Sourlands, and one of the sills we will see called the Byram sill. We have the Passaic Formation, which is shallow lake. Above the Locaton is deep lake, and the Stockton, which is fluvial, braided, and meandering. This is the Stockton Formation. We will see these hand specimens placed into context of the outcrop, and these hand specimens, so these are from the Skews Quarry we will take you to. This is, I believe this one is from the Stockton Schoolyard, which is our last stop. Again, I'm showing you the cores. In this case, the cores, this is the Princeton core hole. Princeton's here, so it catches a little bit of Locaton at the top and then Stockton. This is what the Stockton looks like in a core, relatively unremarkable, but these are the brownstones. So if you ever walk around New York City again, one of the things, the architecture, are the brownstones, or walk around Old Queens campus at Rutgers. The most famous brownstone there is called Geology Hall. Have any of you have you been to Geology Hall, Ronan?
Yeah,
I would think so.
On College Ave, right?
Yeah,
Yeah.
Of course. And what is that made out of? What kind of stone is it?
Arcos.
Yeah, it's Arcosic brownstone. Okay, so that was quarried nearby, all right, in New Jersey, I believe, but it was quarried by the same person who oversaw the building of Geology Hall, which is Hardenberg, Henry Janeway Hardenberg. He's a 3-namer. Henry Janeway Hardenberg, first project was Kirkpatrick Chapel. The second project was Geology Hall, and the third one was the Dakota. Dakota is not in the Dakotas; it's in New York City, right on Central Park West. And its most famous resident was John Lennon, who was shot right outside of the Dakota. But it's a brownstone. But I think most of the brownstones in New York, they quarry the equivalent lower Arcosic sandstone from the Hartford Basin. So they went to Connecticut to get their stones. Okay. Princeton's got a lot of gray buildings. What do you think they quarried to make the gray buildings in Princeton? You think it could be this gray rock?
Yeah.
Yeah, this Locaton. Okay. That's why Princeton looks more imposing. It's gray and dark and castle-like, as opposed to the warm Arcosic sandstones of the brownstones. They just warm your heart, right? So more imposing. But this is the Locaton. And, you know, it's not one uniform lithology. That's what we did when we looked at these trays. But it's mostly a blackish shale to massive mudstone, but it gets purplish and shows these are desiccation cracks. Okay, so when I say it's deep lake, it's not always deep lake. And this is the Locaton again. This is from the Nursery Road core hole. We went through this. I'm just reminding you of it. And this is our Passaic Formation. Okay, used to be called the Brunswick Formation until Paul decided to take the term Brunswick and apply it to the supergroup that it's the Newark supergroup and the Brunswick's group. And this is the Passaic Formation. It's rather boring at times, fizzle shale, but it's got some cool features in it. We looked at those. And that Passaic Formation and more Passaic Formation. And just to remind you, so you can see these enhanced specimens. This is, what kind of rock is this? Kirsty, can you tell me what kind of rock that is? You can see the grains.
Sorry, I'm drawing a blank.
Well, what is this black rock? It's got conchoidal fractures on it. You can't see the grains. Makes up most of the ocean floor.
Basalt.
Basalt, if you're English, yes. Yes, that's basalt. Quite. So if this is compositionally identical. You can cheat, it says right on it. Can you read it? D-I-A.
Diabase.
Diabase, yes. Okay. Yeah, some people crack it open and look, oh, it's a sandstone. Well, no. This is a volcanic rock. Okay. Yeah, Ronan's laughing because that's what he was going to say. Right, Ronan? That's a sandstone. No. This is a diabase. Okay. Hey, by the way, couple hints. All right. So dark rock, like this is like what we do in the field, by the way, because it's stuff that you see that you don't, in a classroom, you forget to say. It was common sense. So this is the Locaton. And yes, you see how this has this conchoidal fracture. This thing's been cooked pretty well. It's pretty, you know, not metamorphic rock, but it's getting there, okay? But in general, most sedimentary rocks don't do that. This black rock is a basalt, and it has very nice conchoidal features on it, okay? Because it's very dense. So the density of this is denser than most. That's another way you can, when you hold it in the hand, you're not holding it now, guys, but you can imagine holding your hand. This is denser than most sedimentary rock, okay? This is also denser, but you can see the grains because it's a sill. It's had time to cool. And by the way, the real difference between, I always say, well, isn't this gabbro? No, it's called dolerite or diabase because it's not as coarse grained as the gabbro, which was born at much greater depths. So we're going to now start our field trip. I talked about these lovely places. This is the town of Stockton. This is coming up. This is probably one of the best cycling routes that I know of, is going up Route 29. We were up here the other day and just Jim and I, Professor Jim and I, are looking at these. And so this is our fourth and fifth stop in Stockton Borough, the Byram Sill, which is where this came from. Byram Sills and Byram, the beautiful town of Byram, New Jersey. There's 4 houses. So this is fairly rural. Coming up to Frenchtown, which is rated the most interesting small town in New Jersey, like the one place you want to visit. So it's great. I always recommend people, if you haven't been to down to New Hope and Lambertville, which is right down here, okay, to the south, or to Stockton, go there for, you know, a Saturday. Hopefully it's not too crowded. But Frenchtown's a cute little town that we always drive through on the way here. And then we continue north through the town of Milford, and there's a good brewery in there, okay, called the Ship Inn. It was the first brewery that opened in New Jersey when they allowed it. And then up to Pebble Bluff, and that's where we're going to start. So, any questions? All right, we're going to start this video. Wait a minute. You can't see that, can you? Let me share. Okay.
Start it over.
I will. I want to, before I start this, let me just preface this by saying a lot of people work very hard to produce this. This is a version 1.0. Lauren Knightsky Adamo, who runs the Geology Museum, took the time out during a very difficult personal time. She just lost her brother, to produce this in a short time interval. This was shot by Lauren and by graduate student Ashlyn Spector, who's doing these online kind of classes and helping develop this as part of her thesis. So you're seeing just a primitive version of this, but it's a good start.
Good morning, and welcome to Pebble Bluff, New Jersey. We are about 3 kilometers north of the town of Milford, New Jersey. Scenic vista on the Delaware River on Milford-Regalsville Road. This has been dubbed Pebble Bluff for obvious reasons. The pebbles and cobbles here making up what wasn't always classically interpreted as an alluvial fan deposit, because it's conglomeratic. It was often dubbed a fanglomerate. And it even had a separate formational name called the Hammer Creek Formation to distinguish it from the rather monotonous, if not boring, shales of the supposedly underlying Passaic Formation. The Passaic Formation, which you'll see in some of the video, is outcrops down here, classically red beds with some very faint cycles in them. What was interesting about these is that Paul Olson from Lamont Doherty Observatory at Columbia University first interpreted these as basically a facies within the Passaic Formation. And although the sedimentologists have always found these deposits here, these conglomeratic deposits, very interesting, when we look in more detail, there's a much more interesting story here. At the beginning, but we are not very far from the border fault. According to Paul Olson, we are 2.4 kilometers from the border fault. And this is material that is coming off of the uplifted block okay, and into this basin, probably through a series of what we call relay ramps, where the streams come in and feed these large streams, and ephemeral flows, debris flows, come in and feed into the basin. The basin, in general, is dry, with exceptions of when lake levels rise. So when this basin is quite dry, a sudden heavy precipitation would result in the release of basically debris flows. When there's more sustained precipitation, you may get small streams depositing flows like this. So the cross-bedded sandstone, okay, and going into more moderately the well-sorted sorted conglomeratic unit. So this is interpreted initially, I think it was by Joe Schmoo, the U.S. Geological Survey, as basically offshore berms in the lake. So shallow lake deposits with wave influence, cross beds, and actually offshore bars of gravel going into a deep lake down here. And we're going to back up and look at the section below this. What we'll see is that succession that goes from cobbles to cross-bedded sandstones to black shales, that we begin, as we come out of the black shale, we see a repetition of that succession downward. And in Walder's law, the lateral variations that we see are vertical variations. So if you zoom in, you can see these cobbles are oriented in all kinds of directions, different directions. It is basically no uniform direction like you would expect in this stream. These are subranded cobbles that have been just deposited probably in a series of debris flows. These may be, in fact, individual flows. Here's one that goes into more of a sandstone, has more debris flow. This may be better sorted and maybe, in fact, more from an ephemeral stream. But this series of debris flows has interested geologists, in particular sedimentologists here at Pebble Bluff, and generations of students have come here and examined these, described the class, and described the orientation. So this is what caught the imagination of geologists. Some of these clasts include Devonian sandstones, classically known in England as the Old Red Sandstone. But in the United States, the counterpart on the other side of the Acadian Mountains, we know is the Catskill Delta facies, which is not one single delta, but many deltas. And the question was always, how did this material come here? It was not transported all the way from upstate New York. And the answer is that there were Paleozoic strata, probably exposed on the uplifted block on the other side of the border fault, and it brought this the kilometer scale away, not the tens to 100-kilometer scale of coming from the Catskills. So that always mystified geologists too, that these purplish, when we get some of these grains, you can see that they are, in fact, sandstone cobbles. Most of them are quartzite. Pointing at the black shale, and as we come down section, we can see this bed consisting of granuliferous, maybe a little bit pebbly, cross-bedded sandstones. This again is returning to the lake margin. And then going down into, you can see this heavily pockmarked surface. This heavily pockmarked surface probably originally had caliche, which is a carbonate deposited as a soil. So there were soils. This was originally a paleosol. And that's telling us that we are then subaerial, no longer in the lake. So think about the succession going up. Paleosol here, a lake margin there, coming up into a deep perennial lake, a lake margin, and then going into fluvial gravels. So what's interesting then as we go down into this bed, we see it pebbly and moderately to well-sorted pebbles in this bed, which is interpreted again as more of a stream deposit. As we go further down, we begin to see larger and larger. So just to remind you, cobbles are from the size approximately of a tennis ball to about the size of the basketball. Most of these large clasts are cobbles. And they're irregular in terms of their distribution. Okay, this is probably just a debris flow deposit. So we went from debris flow deposits to stream deposits to shallow lake deposits to deep lake deposits to shallow lake deposits and back to stream deposits. That's the vertical succession that we see here in this part of Pebble Bluff. We're now going to walk this section and look at the facies along the way. And what's most interesting is that we come back to something similar to this as we move down section. Okay. So this particular clast approaches certainly almost boulder level. So we can see that this material here is particularly poorly sorted. If you look at this, vertical clasts here, this is clearly a debris flow deposit. As you come down though, you see this sandstone, shelly sandstone here, cross-bedded sandstone here. So this is clearly an alluvial deposit. That is to say, stream, alluvial, okay? Moved by water with generally one direction. And then we come back into poorly sorted, look at that, angular grains, randomly oriented. Look at the orientation here versus the orientation here. So we look at the orientation of these grains, they're irregular, random, and this is a debris flow deposit, or as I like to call it, a garbage can facies. Just like you took a garbage can and dumped it upside down, clasts of all different size. The process of debris flow versus the process of a more unidirectional stream fluid flow. So you can see that very irregular bed with clasts in it. Oh, it pinches into a sandstone here. Okay. And then into another cross-bedded sandstone. Okay, you can see the cross-beds here. Cross-bedded sandstone with clasts that have been reworked and into preferentially oriented. This is basically lake margin again. And I should add, it's possible that instead of being a fluvial deposit, that this could be lake margin here. But this is clearly lake margin. You can see the cross beds of the material. The clasts are oriented in one direction. We're coming down, and guess what's here? This is our black shell again. We can dig this out and pull out pieces of the shell. And you can see that this, again, is our black shell, making this invagination into the cliff. So the facies that we see are black shell facies, cross-bedded sandstone, intercalated cross-bedded sandstones, and randomly oriented clasts of cobbles, even going into boulders just above this. So this is a cycle. You take it from the shell here to the shale where we started, we have come from about 14 meters up in the section to about 7 meters in the section. This is about a 7 meters thick unit that we just took you through. And it reflects, again, perennial or deep lakes, a shallow lake margin, debris flows perhaps building into the lake, perhaps some streams going into the lake, or these could in fact just be lake margin with the debris flows building in. And then more massive domination by debris flow. Now think of this in terms of evaporation and precipitation, okay? Lake only exists because there's high precipitation relative to evaporation. It's perennial. As the lake shallows into the lake margin, it then is reflecting, it is becoming drier. And then drier yet as we move into the debris flows. So this cyclicity exists here at Pebble Bluff. We can see this in deep lakes of the Locaton Formation, but we can also see them in a more subtle expression in the red shale facies of the Passaic. This is the conglomeratic facies of the Passaic here. The dominant facies of the Passaic are red shale, as exemplified by anywhere you walk around Rutgers campus. And that red shale also shows cycles, but they're much more subtle. Sometimes they're very difficult to see. And we will look at one of those further down the road in a few minutes. So this is one or more debris flows. It actually looks like to me that there could be a couple debris flows. This is an irregular surface with, you can see the imbrication, no given direction, random. Then all of a sudden, the pebbles here are oriented. This could, in fact, just be an exposure horizon. There's another debris flow on top of it, and then another debris flow on top of it, and then another debris flow on top of it. And we go here into the sandstones here. And these sandstones are interpreted as most likely due to more, again, stream deposits, well sorted. Material in the sandstone is very well sorted, okay? Occasional classed at random angles, but in general, well sorted with the streams flowing in one direction. Again, a little debris flow deposits going down into better sorted, and then another debris flow deposit here. So some of these pock marks are just due to weathering out of pebbles, but some of the heavily pockmarked surfaces are probably reflecting caliche eroding out. And we're going to look for a few of this. This may be one. Contact here with all these pockmarks. This is on a soil surface. This is a soil here with the debris flow on top of it. And then we have a series of, these could be debris flows, they could be stream flows, but you can see there are a lot of these caliche surfaces which are telling you these are heavily soilified. So we have paleosols here telling us that we have mostly exposure of the landscape through time. So as you can see in this outcrop right there, there's heavily brecciated, probably just weathering out of a lot of these caliche horizons. Again, mostly debris flows here. And somebody's drilled in here to put explosives. This is probably when the road was made. This not a burrow, it's a drill mark. So we saw one cycle coming up, and a good question would be, where's this next cycle? So I paced off from the first shale to the second shale, and I got about 42 paces, which is about, with my pace, about 38 meters along the road. The strata dipped into the waterfall by about 10 degrees. So if you do trigonometry, remember that from high school, would be an arctangent about 0.17, which means that's about 7 meters of thickness. So I then paced off another 42 paces, and it brings me here. And we can see there is no black shell, but we have these facies here with the cross-bedded sandstones here. These cross-bedded sandstones could in fact be lake margin deposits again, and the lake never got sufficiently deep to record the black shales. Because mostly as we come up section, using Walder's law, we still see a repetition of facies, but we've lost the black shale. So now we're looking at typical red shales of the Passaic Formation. A few clasts in them, but these are crumbly black shales, some bedding, but in general pretty crumbly. And these are basically interpreted as shallow lake to playa type lake, ephemeral lake, with lots of caliche and soil horizons in them. And we're beginning to get out of the more conglomeratic facies. This is probably when the material was building into the basin. Remember, these are tilted to the northwest. There was some original depositional tilt to them, but the material is building into the basin from behind it. Okay, there's several facies in this spectacular cliff. One is this cross-bedded sandstone, common direction to the northwest, but there are hints of beds going the other direction. We obviously have the conglomeratic unit, looks more debris flowish to me. Clasts seem somewhat random. More debris flow deposit there, and then you see the crumbly red shales up there. Of the typical, what I call typical Passaic Formation, those crumbly red shales. I interpret this as lake margin again, with sandstones dipping both directions, preferentially potentially on shore.
Ken, I muted you and I think it stopped our sound. Can you unmute yourself? Can you unmute yourself? Sorry, I muted you because there was rustling, but I guess it also stops the sound of the video.
Okay.
A small offset picked out by the vegetation. I was remarking to Lauren, the vegetation is very smart and knows where the plants are. It grows preferentially in the fall. So there's a slight offset, just a couple feet. But you can see there is that same cross-bedded unit. And up here, you can see the cross-beds quite distinctly filling in a trough of some sort here. That could be an alluvial environment, but to me, it looks more like it's probably a custom. And then as we go up into this massive cliff with numerous debris flow deposits. So this, to me, is that, again, we've hit one of these lake cycles, caught a piece of it here, as we are about, 3/10 of a mile toward Milford from where we started out. We're now going to go toward the town of Milford and look at the section below, which doesn't have these coarse-grained facies. Okay, we're about 1.2 miles to the south, closer to the town of Milford. So we're down section significant amount. We are now in exclusively red beds with no conglomerates. This is the classic Passaic Formation. It's probably the member that's older than the Perkasie, so we can look that up. But what's remarkable here is, in general, I find The Passaic Formation, about as boring as you can find them. Not great sediment structures, but there are very good sediment structures here. There is a crossbed here in these amongst the shale partings. So this is probably sandy mud, slightly sandy mud here. Okay, so we have crossbeds going like this. And there's even a hint of crossbeds going in the other direction. So they're going this way here, and here there's a little trough. And if you can see the partings going this way, that's the opposite direction. So these are probably the excluded as fluvial. They are shallow lake crossbeds. And if you see this cross-bedded unit, shallow lake, sits on this crumbly fabric. This is what we think of as a classic Passaic. So this is the playa lake, ephemerally covered with water and then desiccated and resulting in this brecciated fabric going into a shallow lake. And if you follow along here, we can trace this bed, and perhaps from the sunlight, you can see the crossbeds here spectacularly developed in this shale. And it is still most likely a shale. There may be a little bit of sand in this. Okay, some of these beds washing out maybe slightly sandier, but it's predominantly a shale. And we can see that this goes up and continues in this shallow lake environments. Some more crossbeds up there. We're going to walk down section now. Walking down will put us progressively further down into the crumbly beds and see if we see a repetition of the faces. This is that same contact between the cross-bedded faces. Again, here's a trough cross-bed. Here's planar to slightly almost in the opposite direction. And here's this crumbly fabric. You actually can begin to see some of the primary stratification. Here, this was certainly a paleosol developed on top of a shallow lake. You can see this part, this bed. This is a bed or a laminate. It's a bed going all the way across. But as we get further up, these have all been solidified. So this is a shallow lake that was ephemerally exposed. And if you continue along, I'm going to walk around the car. This crumbly fabric continues. Beds are fairly slowly dipping. And if you come down to this point here, you begin to see a more, right by this red car, you begin to see a more massive bed here again. And if you follow that along, you can see exposed here. And again, this isn't as spectacular, but this is certainly more of a massive bed, less of this crumbly fabric, faint hits crossbed. So if we look back that way now, if you pan across toward where the car is, you can see much of the cycle right at the foot by the car is the top of the cycle going into the crumbly fabric and going into the crossbeds, and then of course at the very top goes back into crumbly fabric, which makes the talus stone. So that is a cycle in these red, shallow water lake deposits.
And that's it. Let me now. So we're going to start the, Anya, how do we want to do this? We want to go to breakout rooms now and have people start through this exercise, or how we want to do it?
Yeah, we can do that.
Well, let me just take you through a couple things first. So this is a picture taken of Pebble Bluff, and I hope you all have a protractor. You can try to estimate what the dip is.
We only can see you. We can't see Pebble Bluff.
Yes, of course. Meetings, view. No, here it is. Share screen. PowerPoint. There we go. All right, so this is Pebble Bluff. Jim liked this picture. You can see the conglomeratic facies, less conglomeratic facies. Measure the dip. Try to estimate what the thickness is, basically. This is the section from Paul Olson from Lamont. This is from a field guide. And what you'll do is take some time in the breakout rooms and fill out the facies or where these arrows are pointed to. Identify the cycles and measure how thick the cycles are on your own. We're going to continue on. There is a 2-minute video. Let's do that exercise first and meet back in about 10 minutes. Anya, how long do you think it'll take?
I haven't seen the exercise, so I don't know.
There's only 7 questions, so 10 minutes. Okay. Then we're going to go through and visit the next outcrop. Okay. And what I'll do is I'll play the videos and then you can answer those questions there. And then we'll go to the next outcrop. Okay. So let's take 10 minutes and go to a breakout group. So how do we do this?
I can do breakout rooms. I'm just coming in with my computer because apparently my iPad can't do that.
The assignment is posted over on the Canvas site. I don't know if everybody had gotten that.
Did they?
I don't see it.
Yeah, I don't see it either.
I'll bet you I forgot to unlock it.
I got access to it, but that was because I had.
You're a prof.
Yeah, go in and unlock it, Jim.
I always forget to do that. And it's Journey that usually has to send me a notice and say, you forgot to unlock it. It's now published.
Oh, it wasn't published?
No, I forgot to click the little button. You don't have to do that in Sakai.
Get on and show them where that is so they can all download it right now.
It's over in the modules under Newark Basin Virtual Field Trip over on the Canvas site.
Okay, and so there's 2 files there. One, they're both PDFs. One is the lecture I just took you through, and then the rest is the 35 questions that you have to answer. Okay. And what you'll have to turn, let me just show you, Jim made a PDF of this so you can see this. There are questions and we're going to work through this. There's a couple of videos and I was going to walk you through a couple of the different examples. We'll do this by stop. And so we'll take 10 minutes now and work our way through, but there's some 35 questions that you would need to answer. So all you have to do is turn in a piece of paper with the answer to the 35 questions. So the very first question is trace the bedding and measure the dip. So you will have to, I assume everybody has a printer or else can take that. One thing you can do, and you don't have to do it now, but if you want to do it later, you could take a screenshot of the PDF, dump it in PowerPoint and just put, I mean, I think you know where the bedding is, but I just want you to be able to make sure you know where the bedding is. So part of that then was to measure the dip. Okay. Fill in this section with the description of the material. What you have is the very, everybody knows what a facies is, right? So tell me what the facies are for each of those units, okay? And then we'll come back in a few minutes. So Anya, how are we doing this?
I just opened it, so they should be going to rooms now.
How do I get into a different room than you?
I will send you somewhere.
All right. And send Jim to somewhere else. Everybody.
Wait, yeah, don't send me somewhere like nice and warm.
Yeah. I'm going to send you to Saint somewhere. I've been there, by the way, Saint somewhere.
So I'm going to breakout room 2.
And I'm going to
Looks like it's just us. Oh wait, no, here comes everybody.
How we all doing?
It's a little tricky with the cycles.
Well, let me take just a minute. So do you know how many geologists, you may have tens of thousands of geologists came through here and didn't see the cycles? I'm serious. Most did not.
What?
I'm serious. Because eyes were covered by, what do you see here? And we went through this. All right, so here, these were all the size of tennis balls. Okay, so this is basically a cobble layer. And then we have this sandstone with probably some kind of, soil, but then this beautiful feature. So is this one or three debris flows? How many debris flows are in here? Well, I see there probably, Paul did it for us, there's 4 flows maybe. But the key on the shales. So if you key on the shales, you're only seeing you're seeing parts of 3 cycles, but you have 2 shales, and one at 6.9 meters, and one reaches this. If you look at Paul's description right here, yeah, this is all fine grain, but the black is probably only here at about 13.3, 13.4. So this is your cycle. Okay. Interesting facies. We could do a lot of descriptions just from this chart. I mean, here's cross-bedded sands. There's cross-bedded sands, right? This is probably cross-bedded sands also the way he did. He didn't put any cross beds in there, but I would, because we saw it. This is the very first bed that we took you to. This is where we walked down, and I looked up and said, wow, there it is again. Here's the shale. Okay, so that's the cycle. And the reason why people weren't thinking on number 3 here, what are the environments? Of course, this is some kind of alluvial fan, but they didn't realize that there could be a lake here too, and that this is a deep lake, and this is a deep lake, and this is a shallow lake, and this is a shallow lake, and these are debris flows and an alluvial fan. And this so-called fan conglomerate, which is an awful name, is building into a lake. So I hope that helps everybody in their interpretations here. All right, let's go to stop 2. And I got only a 2-minute video here.
Ready? Taping. Okay, welcome to just north of Stockton, 3-4 miles north of the borough of Stockton, about 7 miles south of beautiful Frenchtown, right along the Delaware River. This is exposing the Lockapon Formation. You can see the shaly layers in here. It's quite fine grained, quite organic rich. Then it still stays somewhat fizzled and then becomes more massive and gets slightly as we go up. As we go down section, if you come around here, you can see underneath the shell are these more massive purplish units. The shales are obviously a very deep lake, not stirred by winds. Okay, we actually can get almost barbs in some of those sections. This is a shallower lake where the chemistry starts getting pretty strange, and we get unusual minerals deposited in the purplish bed. And so we're coming up section from that, the shallower lake, into a deeper lake, and then we start to shallow up. We're going to walk along here about 24 paces. And as we walk along, Professor Jim will be shooting some of the strata. The strata are dipping to the northwest at about 9 or 10 degrees.
That's
And
not
we'll be able to
correct. They're
keep
actually
The
13.
thickness of these cycles by basically our pace. We pace this off, and the shales return in about 25 paces. It's a little less than 25 meters. And here we come into a shalier layer here, and then a more massive unit. We can see, and then we'll continue along the north.
We'll come back to these photographs and breakout. I think I have one more video. Yes.
Okay. About 100 paces from where we started in the very first cycle. And at about 75 paces, we didn't see anything. And that was because the lakes got just too dry to get shelled. We then see the next cycle up, about 100 paces is here. This is, again, starting to get slightly shelly. But the nice thing is this clip shows, again, lakes becoming dry and then wetter into these slightly shelly beds and becoming more massive and drying out into the next cycle. So this is the previous cycle going into the deep lake and then drying out again. So what we've just done is come along these essentially five cycles where we didn't see number 4. It's essentially the 100,000 year beat that we see. And if we continue along, we see these cycles repeat along the road. Further down.
I just want to make sure the other video. So this is further along the
How's
road.
your acting, Garrett? I'm going where the vans are, which is the wet of the wet, to where Garrick's standing, where he's standing in the dry of the dry of the dry.
So in this exercise, we're going to take 10 minutes. I just want to place you in this section. We're here in the Skunk Hollow member. And we started here with what's called the fish bed because there are fish in it in some places in the basin. It's the deepest lake cycle. And we found the next lake cycle. And then you didn't see on video, we did. And then we saw, got real dry. And then right about there was where I ended up in the video. What we then did was where that last video was one of the students from our former class. We walked all the way along to here, a quarter mile or more, and stood here where it was this massive cliff. So black is shaly, gray is gray, white in this case is almost purplish, massive units. So we went from very wet. So this is wet part of the 20,000 and wet part of the 100,000, wet, so not so wet, and wet, dry. This is the dry part of the 100, okay? So this is the very first cycle that we did. And then the overall cycle is to go to the very top where this is the driest part. So I use the term dry. So this is the dry part of the 100, the dry part of the 400, but of course this bed here is a cycle boundary and where it got actually just deep enough to make this layer. This is a fairly dried up lake, mostly playa lake. So to remind you what a playa lake is, I checked the definition myself. It's one that's dried up. Now these lakes aren't always dry, but they are generally very shallow and they do dry up. And we will look at features. You'll need to look in the breakout room and tell me what you think these features are, okay? What these features are, and tell me what the facies are and the environment of deposition. So It shouldn't take the full 10 minutes to do this, except that I did throw in this. So I was wrong about the geometry. I went and checked it. You're going to solve for the thickness. So this will take you add that in, it'll take you 10 minutes to answer these questions. So Anya, you want to send us to breakout groups? Okay. How we make out, folks?
How far were we supposed to get on that one?
We finished the trigonometry.
Oh, I didn't get that far.
Okay.
Didn't get anywhere near that far.
Yeah, we didn't either.
All right.
We had a question about the one where it's asking what's the significance of the contact.
Yep.
We can't really tell much from the photo. Is that one of the contacts where there's root traces coming down from it?
Yeah. Perhaps. What I think you can guess. So if you look at this, about 12 feet thick, about 4 meters. Okay. So the cycles that we are mapping and looking at, and if you do the arithmetic, which is this figure here. By the way, I should point out, it doesn't say when I took my group through, the actual dip at our locality, which is shown here in the red, is 13 degrees. Okay. Those are probably cycle boundaries. Okay. These are shallowing up lake cycles where the top of them do look like this. Did everybody get that these are mud cracks and hence this is an exposure surface? And then that means that this was a playa lake, which is a lake that's dried up. That's what a playa is, but these were shallow lakes that went into a playa lake. So this is the top of the cycle and then it floods back in again. That's really what we're looking at here on these contacts. So when you fill this out to turn it in, the answer is that these contacts are in fact lake level cycles in the dry part of the cycles. Okay. And so most of these are pretty straightforward. The facies, of course, these are shallow. These are desiccation features. So the environment again is shallow, very shallow lake to playa lake. Okay. These are desiccation features. These are in fact desiccation features. These are some desiccation features here. So it's a femoral lake and then a playa lake. There's probably also a playa lake here. So it's very shallow in this upper part of the cycle. Okay. Very shallow. This is one of those cycles. This one still has some shale in it and it's the shallowing upward part of the succession. Here, we're not getting any of the shales except perhaps there. That probably is a shalier interval. Okay, so that's why it's telling us it's a cycle boundary. That's what I wanted you to guess at, that it is probably a shale. Okay, and so that's where you get, but it probably does look very much like, where is that? This one, where we have desiccation features and then it floods in. All right. Let's, if anybody has questions about this, this is how you figure thickness out. We need to know my pace. I calibrated. You will need to calibrate your pace before you go into the field. Okay, so this is my pace. It's not going to be exactly yours, but I computed that the distance along the road was 18 meters. I want to compute the true thickness, right? Not the apparent thickness of the bed, the true thickness, which is the perpendicular between this one and this one. So this is a right angle and this is a right angle. This is theta, which is the dip angle. Theta is given here. Simplest thing, I wouldn't trust yourself on a calculator because if you put in a trigonometry and put in 13, they'll assume it's in radians and you'll get some weird answer. You look up the sine of theta on a table, it's about 0.22, and you can figure out the thickness. And the thickness is roughly 4 meters. So then we said, what is the thickness? My group didn't get here, but what is the thickness? If it's 4 meters, important thing to realize that everything we've been talking about is a 20,000 year cycle. 20,000 year cycle. 20,000 year cycle. So if I ask you what the thickness of a 100,000 year cycle is, you should be able to do that pretty easily. And that makes a prediction. Just from the little observation we got, read off of this and tell me what the actual thickness of the cycle is. Okay. So you can take a ruler, put it against your screen if you want, but it's on the order of 20 meters. And in a 400,000 year cycle, yes, you could take 20 goes into 400. Yes, it goes in there 20 times. So it'll be 80 meters, but measure it off, and it's about that. So this one's just for fun. This is a little stop just south. There's a little pull-off area, nice area on the Delaware River. This is actually right at this place is where I proposed to my wife. It's a lovely place in season. Okay, and I'm just going to play the video.
We are taping. Good. I asked my wife to marry me at that spot. And we're panning over here. This is the Locaton Formation. Now right here, it's a little bit cooked, but you can see it's dipping to the northwest. There's some shales in there, some more massive beds. This is Byram, New Jersey. And when you're looking at contact metamorphism with Byram sill. So pan over there, you can see this is Locaton. And then up there, you can see that there is a buff tan-colored, vertically jointed system. And system meaning it's a big series of rocks that are vertically jointed. And there's a contact in between. You walk along with the camera, see it again. So we have Locaton to the left. And we have this big blob of gray dark rocks. And then we have the tan buff rocks right there. Your objective in looking at the photographs is to pick the contact. And again, vegetation tends to be pretty smart in helping pick the contact.
So we'll go to breakouts now for 5 minutes, Anya. If we could. Can you hear me? Yeah, okay. How'd everybody make out?
Good.
Good. So we ready to go? Is everybody back? Anya?
I think so.
Okay. So this was the contact between the Byram sill and metamorphosed Locaton, called the Locaton. And again, this is the sill, this vertical patterns called jointing. This is in the diabase. This is similar to the, very similar in composition to what you see in the Palisades sill. This is a sill. This is the Locaton. Okay, dipping to the northwest. And we'll move on. We'll move down a couple miles to the town of Stockton. This is, I managed to get myself back into Skew's family quarry. These are pictures that we had seen before. So we're gonna go to breakout for 5 minutes and just do this particular outcrop. There's some pictures to show you, first of all, what is the lithology here, what kind of rock that is. This picture, the color is not as faithful as perhaps you'd want, but it's actually a very good illustration. I want you to pay attention to this feature here. Okay, this is a channel. These rocks are from those various places in the outcrop. Okay, yeah.
That picture with the pencil on it, where is that found in the outcrop?
I believe that's from right in here.
Okay.
Okay, I didn't point that out, but that's why I'm going through these, make sure we point out all the features. Again, I'm guessing that this was down in here. There were some, this is hematite rich layers in this. These are chips of mud, okay, in a matrix. This is a nearby outcrop. And what I do want you to do in both of these is more or less trace the bedding and the grains and the trend in grain size. Do the same thing here, just where the beds are and what the grain size does. And that's what we'll do for 5 minutes, okay?
I'm redistributing.
And do you have a scale on that? You say how thick?
Yeah. On this, let's just take this unit from here to there as being 10 feet,
Okay.
just for this exercise. And here, I would take that as 4 feet. Okay? We should,
Oh, okay. It's that thick?
yeah, it's pretty thick, actually.
All right. Didn't look it. But I'll
It's
take your
3
word
or
for it.
4 feet. I didn't, I should go back. This is, if you go to Stockton, it's a lovely place. You can't easily get into this Q's quarry, and it has more no trespassing signs than I've ever seen before in my life. And we used to have permission to go in there, and then they decided just to close it all off. And if you park in front of the on 29, great place to cycle, great place to walk. But if you park, the police are there in about 3 nanoseconds. But you are allowed to park at Prowsville's Mills, which has a little art gallery, and it's kind of a cool place to visit on a Saturday. And if you walk behind Prowsville's Mills in the north part of Stockton, this outcrop is right on the bike path. There's a wonderful bike path that connects all the way from Trenton all the way to Milford, New Jersey. It's the former towpath of the Delaware-Raritan Canal. And it's great for cycling or hiking or walking. And this is right on the bike path. But I haven't been back here to actually calibrate this. I didn't, normally we go there ourselves. So take it 4 feet.
I've redistributed people because we had 4 breakout rooms and there was only one of me, so it's better now.
Okay. I'll join a breakout room. So Jim Wright, or Jim Browning? Can you hear me?
Jim Wright is not here. I
Jim
can.
Browning's not here? Okay, good.
This is our last stop.
Yeah. Well, we'll have to wait for, is everybody here? Oh, yeah. All right, so everybody's here. I just wanted to point out to Jim something I never noticed before, but so I drew the arrows helping people out and showing you the finding upwards from the sandstones to the shales, the sandstones to the shales. One of the things that I didn't realize before, even looking at this in the field, is that these things are stacking such that they're getting a little bit thinner up section. In the previous outcrop, so this is certainly finding upward here. This is a point bar. This is a meandering system. It's about 20 feet thick at least. This is a channel, an erosional channel. And in the erosional channel are these mud chips. So this is, we take as a classic example of a meandering river system as exposed here at Skews Quarry, to a certain extent here at Prowlesville. Remember here, they're not quite as thick. This is about 8 feet. This is 6 feet. This is 4 feet. This is roughly 4 feet. So they're not as thick point bars as this is a pretty thick ass point bar right there. So let's go to the last stop. And this is the Stockton Burroughs School. We've been here when the school was in session. It is now permanently closed, unfortunately. Not just because of COVID. It's a 3-room schoolhouse, and if you lived in the area of Kingwood Township, and you may have gone here as a kid, and actually a couple people in the New Jersey Geological Survey, their kids went here. I saw them there when we were visiting the outcrop right back here. So it's a really scenic and historic place. So this is the outcrop. You can see, so first of all, it's a bit more conglomeratic, and I guess I'll introduce it here.
Yeah. Welcome to the Stockton Schoolyard in Stockton, New Jersey. This is one of the oldest formerly operating schools in New Jersey, now closed permanently here. It's a 3-room schoolyard. Many times we've been here, it's been active. This is a nice exposure of some conglomeratic units that are a member of the Stockton Formation, which is usually considered an Arcosic sandstones we saw at the previous outcrop. But here you can see it's a conglomeratic unit. If you pan up that way, you can see bedding. Now, the road right behind us runs basically north-south, so the beds are dipping to the northwest as they do throughout this region. We can see dug out over there some finer beds, and those finer beds are in fact a mudstone. You can see here, this is a mudstone. So that's a contact there with a channel with the coarsest material at the base of the channel and finding upward. So the scale of these channels probably approximated from there to there. So this hammer is 1 foot. So these channels are about 2 to 3 feet thick, slightly less than a meter. There's an unusual bedding plane here. It probably is an erosional feature at the base of a channel.
All right, so let's just take 5 more minutes and finish up and go through these questions. So we'll go to breakouts one last time.
Evidently, Professor Miller was not ready to come out of his breakout room yet. He's still explaining what everybody is.
I've been telling them the trick questions when I'm there and they're doing them. Sometimes I'm not there, so they don't know about it.
Do what? I've been helping them with everything.
Okay. Yeah, I've been
I've been
telling.
helping them with everything.
I mean, I've been helping
Can't
them,
get-
but I've been telling them the trick questions that they would have no way of knowing if I didn't tell them.
Yeah, well, that's fine.
Okay.
Well, I only tell them the easy ones because those are the ones I know.
I also don't remember all the answers, so when you guys are grading, remember.
Well, then we'll let you grade.
You can grade. They all get A's. Well, let me just wrap this up. We're at 4:30 now. I don't want to beat the hell out of this. Let me share the screen and share the PowerPoint. All right. So first of all, before I end, I just had to point out this slide. This is in this last stop that we just did. This is basically a braided system. It is conglomeratic, lots of quartz pebbles, not much feldspar. It is fairly poorly sorted. I already told you that these are about 2 to 2.5 feet thick. This is finding upward within there. This is a mudstone. It may be a thin soil horizon, or it could just be part of a fine bed, but there's not much mud in this system at all. The thin successions and the lack of mud points toward more braided versus the previous stop. And those are the answers to the question, but I had to point out this figure here. This was our class from a number of years ago. Melissa Boyd's finishing up her PhD in our program. This is my son, Rob, who was in our class and is a geology major and now works for a hydro firm in New Jersey. And Helen Janishishku here received her PhD from Columbia and is now a professor in Hawaii. And this is Mike Lovett, and I skied when he came out and visited me and skied with us this past year. He just happened to show up. He's now a chiropractor, not a geologist. So there's different career paths for everybody. A lot of people have made use of their geology. Other people have done other things with it, but I just thought that was a cute figure. And again, to compare to this, here the successions fine upward, follow that arrow, and that's what you got to do on your screenshots of the figures and finding. I did it that way just to draw the eye, but I would probably say, oh, okay, this is finding upward like there. The arrow's pointing in the finding direction. But this whole thing finds upwards and about 20 feet thick, 6 meters. This is a classic meandering system. It is more arcosic sandstone. That's what you should get out of this. You can see the grains, sandstone, but it is, more arcosic. Again, this why it's so hematite rich, lots of hematite. I should also note that there are these black layers in here, which are specular hematite. So it is basically very iron rich environment. So this was the field trip. There's questions here for you all to answer. And a couple of these, we ask you to take the figures. You can just screenshot them and print them out, or screenshot them and put them into a PowerPoint, do your interpretations on that and submit that if you don't want to do it on paper, which is fine. So not as good as being out there for real. And it would have been lovely to have been out there today. And it would have been horrible to have been out there when we were out there on, what was it, Monday, Jim? Or was it Tuesday?
Yeah, it was Monday.
Monday, yes, Monday. And quite cold. So, but it's a wonderful trip. And I hope this worked in giving you a flavor for the Newark Basin. Questions? All right, guys. So I wish you all a good weekend.
Thank
I have
you,
a
Ken.
question for Anya about lab in general.
Okay, I'm gonna sign off, guys. I was supposed to be in a meeting an hour ago, but that's all right. This is more important.
What's up?
So next week on the syllabus, it says we don't have lab because of Thanksgiving.
Yep.
And then I also want to double check as it's getting closer to finals. Do we have a final for this lab or no?
Not for the lab.
Okay.
No, and I'm catching up on my grading. I'm done with almost everybody for the correlation lab, and I'm working on the next two. I'm hoping to have them done for you guys like by Monday, so you can check what your lab grade is.
Okay. Sounds cool.
If there's anything weird in there, let me know. Sometimes people turn things in late, and I don't know to go back and grade them. So yeah, but I'll see you guys in a couple weeks. Otherwise.
Thanks, Anya.
Thank you.
Thanks. Bye.